our next speaker is Lucía Cabrera. She's a PhD student from Instituto Balseiro in Argentina, and she will be talking about off-string field theories and hidden symmetries. Thank you, Lucía.
Thank you very much. And well, of course, I would like to thank all of the organizers very much for giving me the space to talk a little bit about some work that I've been doing together with my advisor, Gerardo Aldazábal, and collaborators, which is also based on some work that my advisor previously did with collaborators. So let's see why we're interested in stringy field theories. So I'm going to try and motivate this. So first of all, as we all probably know, string theory has as its fundamental objects one-dimensional objects, which are strings, of course, which when looked at from energy scales, which are much lower to that of the string, are seen as point particles. And point particles, we do know, are described by quantum field theories. So string theory is effective field theory is 10-dimensional supergravity, but of course, if we want to get a more phenomenologically interesting theory, we need to get rid of some of these extra dimensions, and we do so by compactifying. And one very interesting feature is that the effective theory that we get does not only depend on the topology of the compactification manifold, but it will also depend on some other things, and this is where the stringy part comes in. This will be due to gauge symmetry enhancement, which is a purely stringy phenomenon. So let's go into what I'm going to be talking about today. So I'm gonna be talking about formulating an effective action for an effective field theory action that will include stringy features. We're gonna do this for the heterotic string, and we're gonna be compactifying on tori. We will incorporate the stringy features through Kaluza-Klein momenta and windings. This will allow us in turn to have gauge symmetry enhancement. We will see that this action effectively interpolates among different gauge theories, which might actually be hinting at some underlying structure of the action that we're going to go looking for. So let me now talk a little bit about what gauge symmetry enhancement is in a very schematic way. As we already said, this is a purely stringy phenomena. It depends on the possibility that the string can wind around the compact dimensions because it's a one-dimensional object. And well, as we already said, also, we will not only be caring about topology, but we will also be caring about the moduli, or the moduli that are kind of like the parameters of the compactification manifold. So what's the anatomy of a moduli point, let's say? Well, we're going to encode them into this phi, and they will be the background metric, the antisymmetric tensor, as well as Wilson lines. And since we have three of them, we can think of these moduli as being in some three-dimensional moduli space, as I've tried to demonstrate with this diagram. So generically, for the heterotic string compactified on tori, we have a very generic gauge group, U1 left to the R plus 16 times U1 right to the R. So if we were to situate ourselves with our theory at any standard point on modular space, this is a symmetry group that we would get. However, there will be certain special points. Let's say one of them is this phi 01. So let's say we're approaching this point with our theory following this arrow. As we approach the point, the symmetry enhancement point, there will be some vectors of the theory that will start to become lighter and lighter. And at the point itself, they will become completely massless. And so together with the already present massless vectors of the theory, they will arrange themselves into some representation of a bigger group, G1 left. And so we will have symmetry enhancement to G1 left times U1 right to the R. And as we move away from this enhancement point, we will have a sort of a Higgs mechanism, and the symmetry group will break, and we will have again the generic group. So let us now move on to the effective interpolating action and schematically how we build this. So all of the kinetic terms and interactions can in principle be read off of 3-point amplitudes of massless heterotic string vertices. Here we can see in this little table the vertex operators and the fields that they correspond to. And all of these fields carry a certain momentum L, which will be a generalized momentum. And this generalized momentum depends on two very important things. So first of all, this phi is the moduli point in moduli space. But it will also depend on these P, and these P are generalized Kaluza-Klein momenta. And we will be caring about the part of the generalized Kaluza-Klein momenta that has, of course, the actual Kaluza-Klein momenta as well as winding numbers. Also, this generalized momentum will need to satisfy a level matching condition that depends on the number of left and right oscillators. So again, in principle, by computing all possible scattering amplitudes, we would get a full action for the heterotic string, and this would have all kinds of fields with all possible spin numbers and all possible oscillator numbers. This action would have infinite terms, but our purposes here are a bit more humble. We're going to split this action into 2 bits, and we're going to focus on the enhanced part, as we would call it. So in here, we will consider terms of up to order 3 in the fields. We will have our fields inherited from the 10-dimensional Kaluza-Klein reductions, so G, B, dilaton, vectors, and a Cartan scalar. And we're also going to be considering up to 1 oscillator on the left part and 0 right oscillators. Then we will also have to add by hand another vector and a scalar, which will both have 0 oscillator number. And we will also need to add a non-commutative product. This will allow us to have non-abelian gauge groups, because otherwise the heterotic string compactifier on toroid only gives us abelian gauge groups. And on this S prime here, we're gonna just be throwing all the rest. So terms of order above 3 in the fields, oscillator number higher than 1, all in all, an infinite amount of terms. So this is what our action looks like, and this action is built in the spirit of double field theory. In what sense? In the sense that all of the fields present depend on 2 things. First of all, extended space-time coordinates, so d space-time extended coordinates, and a set of compact coordinates. So these compact coordinates, we will have a little bit, which is the heterotic degrees of freedom, and then we will have what we will care the most about, double set of coordinates. So this y's m will be the usual compact coordinates, which are conjugate to Kaluza-Klein momenta. And these y tildes will be conjugate to winding numbers. So we actually see that the Lagrangian that we get, since we're integrating over compact coordinates, will be d-dimensional. And we're actually introducing here the non-commutative product in this little star. So how do we work with this action? So if we were to take any of the fields present in the action with oscillator number n, we can perform a generalized Fourier expansion where each of the modes are d-dimensional fields carrying momentum L, where this L again runs over all those L's that satisfy level matching condition. And if we wanted to isolate one of these modes and just study it in particular, we could just perform a sort of inverse Fourier transform. Why did I introduce this? Well, because we want to have a look at what the expansion of the star product looks like. So as terrifying as this might seem, is quite straightforward. We have here the product of the 2 fields, and the noble bit that we have is this space here. So in here, we're introducing the Kaluza-Klein momenta of the field phi, as well as the winding numbers of field psi. And on the second line, what we're doing is rewriting this phase. So if we were to rewrite this phase in terms of what the product between the generalized momenta L phi and the generalized momentum L psi looks like, we would see that it splits into these 2 bits. So first of all, to the leftmost part, we have what looks like the general expansion of the commuted product, and we have an overall phase depending on the overall momentum L, oscillator number of the field phi, and oscillator number of the field psi. So this overall phase is what will tell us whether the product is commutative or non-commutative, depending on the fields that we're talking about. And this will be very important when we're building terms such as field strengths, where we will have or need more like anti-symmetric terms like this one. So let's move on now to the contents that we have on our enhanced action. Let's have a look at the scalar kinetic term. Since this term will contain the two fields that we added by hand, we have to build it actually. We cannot read it off any vertices. But we can do that. We can propose certain derivatives or would-be covariant derivatives. We will have a look at that at the end of the talk. And these are all in terms of the star product. We have the covariant derivative for the charged scalar field as well as that for the current scalar field, which is hidden kind of inside this generalized metric as the first correction to the constant term. And if we look at these expressions with some love, let's say, we can see that they sort of have the structure of a typical covariant derivative. So let us now move on to a little bit of an example where we apply this action. We will have a look at a compactification on a two torus. So we're compactifying two dimensions. This means that we will have a pair of Kaluza-Klein momenta and a pair of winding numbers. But since we also said that we not only care about topology, we will choose a very specific moduli point. So our G will be the Cartan matrix for SU3, similarly with B, and we will be taking 0 Wilson lines. And for this particular case, we find that the ternary group on the bit that we're looking at gets enhanced to SU3. And actually, all of the massless vectors at that point arrange themselves into the adjoint representation of SU3. But however, we can ask ourselves what happens with massive levels. What can we say about them with this action that we've proposed? Well, so we take the first massive level that corresponds to this collection of Kaluza-Klein momenta and windings, and we see that it has mass squared equal to 4/3. So if we were to build the representation from there, we will find that the fields arrange themselves in the sixth representation of SU3, where we will have for oscillator number equal to 0, we will have 3 fields for weights 1, 3, and 6. And for oscillator number equal to 1, we would have, and for weights 2, 4, and 5, actually 2 fields per weight, since this M index runs up to 2. So what can we do with these then? Well, we could in principle mode expand the covariant derivatives that we proposed, or the would-be covariant derivatives, which in principle might look nothing like a covariant derivative in the usual sense. And in here we have hidden the phases that we've talked about before into these Fs. But what we can do is require that they do look like covariant derivatives, in fact, in the current val basis. We find that when we do that, actually there is a way, and we find that the physical fields for weights 1, 3, and 6 are actually just the scalar fields that we introduced in the first place. And for the current fields, the physical fields corresponding to weights 2, 4, and 5 are linear combinations of the fields, where these alphas are the simple roots of SU3, and these M's are contracted. And while these factors here might seem like a little bit random, there's actually a way to write them in a more general form in terms of the phases that come out of the star product and the group's generators. So what have we learned from this example? Well, we've seen that our action can actually interpolate among different gauge theories. We've seen, or we haven't seen, we might think, let's say, that these gauge groups and the fact that the action can manifest different gauge groups at different enhancement points might be hinting at an underlying structure. And what we can do from there is take the SU3 enhancement as a starting point and say, well, we were going to propose some transformations for our fields and see what we get out of that. So we do that. We propose transformations for the scalar fields. And actually, we do find that when we move to an enhancement point and perform the generalized Kaluza-Klein expansion and considering the physical fields, we do, in fact, reproduce a usual gauge transformation. So now we're going to move on to have a bit of a look at what this hidden symmetry is. And I'm going to lead with this quote from Borges that I like very much. So let us go there to the hidden symmetry part. We've already proposed some transformations for scalar fields. These include these gauge parameters that are kind of just like the fields. They depend on the extended and compact coordinates as well. And we can mode expand them at enhancement points. And we've already seen that these kind of work. We can also say that these expressions, up to what is possible, look similar to usual gauge transformation. And we actually already said they do contain typical gauge transformations and enhancement points. Furthermore, we will need to, of course, propose transformations for the gauge vectors, and we can do that. Again, these have a similar structure to a typical transformation for the A nu. And actually, we do find that these transformations allow us to have covariant derivatives at enhancement points. That is to say, they transform as the fields. But we can take it a little bit further and say what happens when we do not mode expand. Because we've always been talking about going to enhancement points, mode expanding. What happens if we keep the star product? Well, we have so far built a toolbox. We've proposed expressions for the covariant derivatives as well as for transformations. And a new approach to this would be to say, okay, I'm going to take the expressions for the derivatives and the expressions for transformations and vary them term by term. I will get something, and then I'm going to leave that to the side for 1 second. And I'm going to take, again, the derivatives, and I'm going to say, okay, I'm going to assume that these are covariant. That is to say, they will transform as the fields, perform another calculation, and then take the two things that I've calculated so far and try to match term by term. And this is, of course, what we did at the beginning. However, there's a little bit of a nuance in this because there will be tricky terms. So for instance, a very simple term like this, so a product of three fields on the side where we assume covariance will actually be in correspondence with two different terms that look in principle nothing like it on the term by term side of the calculation. So we will need to do a little bit of a back and forth with mode expanding and non-mode expanding to check what terms correspond to what and put everything into a one-to-one correspondence in a sense. And there will be actually many of these trig terms. However, after some work, we can actually call covariance of the derivatives that we proposed in the first place, even without mode expanding. That is to say, they do transform according to the transformations that we proposed for the fields. So what did we achieve with this? Well, we proposed an effective field theory that incorporates stringy features. We've done it for the heterotic string compactified on toroid. We've done it inspired in double field theory. We've done it for both massless as well as massive fields. And our action does not explicitly depend on the moduli point because this is encoded in the Kaluza-Klein momenta and winding numbers. And these only come out after we perform a mode expansion on the phases that I talked about. The action continuously interpolates among different gauge theories. It includes enhancement to non-abelian gauge groups through the non-commutative product. And its would-be symmetries seem to include gauge transformations. And let's not forget that we've done all of this with a truncated action. We've thrown away an infinite number of terms. So what are some possible roads to take with this work? Well, first of all, we need to fully verify that our action is invariant under the transformations that we proposed. So far, we've only checked that the derivatives are covariant and a little bit more, but this is a key point of this work that we're gonna look into in the future or are looking into now, let's say. Another thing is the physical origin of this star product. Well, we know how to use it. We've used it successfully. We don't necessarily know its meaning yet. We could also look at higher oscillator numbers, always using gauge invariance as a guide to build whatever terms we might need, as we've done so far. And there's also a potential connection with double field theory, and these phases that we introduced actually seem to be related very directly with the structure constants of the Cardinal algebra, even when we move outside of enhancement points. So this is a very interesting thing to consider. And these are just some of the possible outlooks of this work. I'm gonna wrap it up here, I think, and I'm gonna thank you all very much and open up the space for any questions you might have. Thank you.
Thank you, Lucia. Thank you for a very nice talk. So please, questions for Lucia.
Hi, I have a short question.
Good.
Yeah.
So actually, like the symmetry enhancement that you talked about, so that symmetry enhancement is in the parameter space corresponding to the compactification, not on the compactified, I mean, in certain points on the compactified space time, right?
Sorry, can you repeat? I didn't understand the last bit of your question.
So I mean, you were talking about symmetry enhancement at certain points. So those points are the points corresponding to your like parameter space of the compactification, not some points. No, I mean, not some space-time points in the compactified space-time.
Yeah, so sorry, I don't understand the question. So yes, we have enhancement that depends on, sorry, I'm gonna look for it quicker this way. Let's go back to that slide. Yes, so we're considering specific points in moduli space. So
Okay, I got it. Yeah.
okay,
So basically, like points means points in the moduli space, not in the space-time point.
yeah, yes. Sorry, that was a question I didn't understand before. Yeah, so yeah,
Okay.
specific points in moduli space. Yes.
Okay. And another short question is since you told like the symmetries you got includes the gauge symmetries. So like is there any way to we can see that large gauge transformations here?
To see what? Sorry.
Large gauge transformations. Like I mean when you study asymmetric symmetries and all, we like see this large gauge transformations and their effects. So can we see that thing also here?
Oh, I don't know really. I'm not really familiar with that. Sorry, I don't know. Would be very interesting to think about it. Sorry, I don't
Okay.
know.
Yeah, okay, sure. Thank
Another question. One last question for Lucia. Okay. If not, we thank Lucia again. Thank you, Lucia.